Alright, this is AP Physics 2 2024 free response questions, the third problem. This is a circuit problem. A circuit consists of an ideal battery of EMF, epsilon, and 4 identical resistors, R1, R2, and R3, and R4, each of resistance R, as shown in figure 1. For parts A first and A second, express your answers in terms of numerical values epsilon and R only. Derive an expression for the current I1 in the resistor R1. So we have to find what is the current one passing through R1. We can see that the R1 is located on the main line. The same wire is passing through the battery. So if we can find equivalent resistance of all resistors, we can calculate easily the current passing R1 using Ohm's law. So let's start with equivalent resistance of R3 and R4. Because they are in series, we just add them up. R3 plus R4 is 2R, because each one is R. Now R3 and 4 are parallel to R2, so equivalent resistance of R to 3 is going to be equal to 1 over R2 plus 1 over R3, 4 to the power of minus 1. Let's put the numbers. 1 over R plus 1 over 2R is 1. So it's going to be 3 over 2R. A bit, it's going to be 2R over 3. Now, all these are 2, 3, 4 are in series to R1. So total equivalent resistance of all resistors is going to be R1 plus R2, 3, 4. So R plus R over 3, it's going to be 5R over 3. All right, we have the R equivalent. Now we can use Ohm's law to find current on 1. Current on 1 is going to be equal as the current on the battery. The battery has got voltage of epsilon over R equivalent, so it's going to be 3 epsilon over 5R. Next, derive an expression for the current I3 in resistor R3. So we have to find what is the current passing through R3. Now, before going on, let's define some potentials. Let's say the potential R2 is dV2 and potential across resistors R3 and 4 dV3, 4. And of course, potential across R is going to be dV1. So we already know the current 1 and resistance 1. So we can start from there. Potential across the resistance 1 is going to be current 1 times R using Ohm's law. So it's going to be 3 epsilon over 5. Next, potential across second resistance is equal to potential across the resistors 3 and 4 combined, because they are parallel to each other. They are all going to be, if you use Kirchhoff's loophole, the battery voltage epsilon minus potential across resistor 1. So it's going to be 2 epsilon divided by 5. Now we can use again Ohm's law. Potential across 3 and 4 going to be current passing through the resistance 3 times equivalent of resistors 3 and 4, because we are looking at the potential difference across both of them. I3 is going to be potential difference divided by resistance, so it's going to be 2 epsilon divided by 5 divided by 2R, so it's going to be epsilon over 5R. Next, Part B. The partially completed bar chart in figure 2 shows a bar that represents the absolute value delta V of the potential difference across the ideal battery. In figure 2, draw a bar to represent delta V across each resistor relative to the EMF epsilon of the ideal battery. Good. The height of each bar should be proportional to the value of delta V represented by that bar. If delta V is 0, write 0 in the column. Now, earlier, we already found what is the potential across resistor 1, resistor 2, and 3, 4 combined. We already know that delta V1 is equal to 3 epsilon over 5, and delta V2 is equal to delta V3, 4 combined, 2 epsilon over 5. So let's start with R1. It's going to be 3 over 5 epsilon. R2, 2 over 5 epsilon. And R3, together they are making 2 epsilon over 5, but they are in series. So, and they are having the same resistance. That means they are equally sharing the voltage. So each one will have epsilon divided by 5. A student claims that the rate at which energy is dissipated power by the circuit can be expressed as E is equal to 3 epsilon squared divided by 5R. Part C. State whether the expression for P is correct or incorrect. Justify your answer by referring to derivations from part A or the bar chart from part B. Now let's remember the power equation. Power is current times voltage, right? If you want to eliminate current, Ohm's law, current is equal to potential difference divided by R. In that case, it's going to be potential difference squared over R. So generally, the form looks okay. But what about the quantities? So we have got in the battery the current which is equal to 3 epsilon over 5R, and the R equivalent is equal to, the current is 3 epsilon over 5R, and changing potential equal to just epsilon. Perfect. We can just use that to justify our answer. So in that case, we have current 3 epsilon over 5R and changing potential as epsilon in the main battery. So if you multiply them, we are having the same result. So yes, the expression is correct. Battery is producing power which is equal, E is equal to current times changing potential. From part A, we see that current was equal to 3 epsilon divided by 5R, and changing potential is equal to epsilon. Therefore, power is equal to current times potential difference, which is equal to 3 times epsilon squared divided by 5R. Next part. When the ideal battery is connected in the original circuit, the rate at which energy is dissipated by resistor R1 is P original. The ideal battery is now replaced with a non-ideal battery of EMF epsilon and internal resistance small r to form the new circuit shown in the figure. So we can see that there is another resistance small r in the circuit. The rate at which energy is dissipated by resistor R1 in the new circuit is P new. Indicate whether power new is greater than, less than, or equal to power original. Well, Now here we can use again the power equation, which is current times potential difference, or if you want to eliminate the potential difference, it's going to be current square times R. Now, if we are adding a resistance to the circuit, logically we are increasing R equivalent. And because we are increasing R equivalent, we are reducing the current on the main line, on the battery, which is also passing through R1. So because we are reducing the current, but resistance of R1 is staying same, power dissipated by R1 is going to be less than the original one. So answer is this. Let's justify it. The internal resistance R reduces the current flowing on the circuit. Since power is equal to current square times R, the energy dissipated by R1 in the new circuit, which is P new, will be less.